Okay, let's welcome Dr. Carvou.
Thank you, Jerry, and thank you to CSBio to invite me to give a talk today. I'm Nicolas Carvou, the Scientific Applications Director for Biospace Lab, and today I'm going to talk to you about a new dynasty of optical imaging systems. So I realize I'm the last speaker before lunch, and we're already running late, so I'm going to try and keep my talk really quick. So I'm going to do a very short presentation of the system this lunchtime, and this afternoon I will be giving a presentation on recent publications and current applications using our system. So just a short presentation of our company. Biospace Lab is a French company that was founded 30 years ago by the Physics Nobel Prize Georges Charpak, who had the brilliant idea to apply his Nobel Prize winning technology of the multi-wire avalanche chamber to imaging autoradiography sections of medical samples. And since then we moved into optical imaging 13 years ago using the technology of the intensified CCD camera, which I'm going to get into more details just now. So we have a very different innovative approach to optical imaging using the intensified CCD camera, which gives us real-time capabilities, and we have a modular system which allows us to adapt the system according to your application. Our technology is already used worldwide by many prestigious academic centers. So here the Photon Imager with its 3D capabilities, real-time quantification. We also have modules for in axial, looking at live animals. We also have microscopic resolution with high definition modules. We can do X-ray for up to 5 mice, and we also have a tomofluorescence module. All these modules can be fitted in a standard system, which will do optical imaging in bioluminescence and fluorescence, but with a difference. And the difference is due to our intensified CCD camera. So if you want to talk about optical imaging, you want to talk about low light genetic reporters or optical reporters. And the problem with low light reporters is how you get the signal above the noise of the CCD. Okay? So the traditional approach is to use cool CCDs, and the reason why you cool your CCDs is to reduce the thermal noise, the dark noise of the CCD, in order to get the signal coming above the noise of the CCD. And the other problem with cool CCDs is that you have to wait a long time to have enough integration of the signal to get above the dark noise. Okay? So another approach to this is the photon multiplier. The photon multiplier is a clever piece of kit that photon multiply every photon that comes into it 100,000-fold going through multi-channel plates, and then is then collected to the CCD. So the signal is already multiplied before it's collected to the CCD. And the signal is much higher, the specific signal is therefore much higher than the dark noise. And therefore, we don't have to wait in order to collect the information. We can collect it from the first frame of the camera, the first second of acquisition. And what does that give us the capability of? Well, I don't know if you have done any optical imaging in bioluminescence yourself, but you know that in a traditional experiment, what you will do is you will integrate for about 10 minutes, and at the end you will get one image. And I don't know if you've ever done those kind of experiments, but when I've done it with a traditional optical imager, I've always wondered what's happening during those 10 minutes. What's happening? Would it be nice to have a system that would allow me to know what's happening during those 10 minutes of integration? Well, the intensified CCD camera allows you to get this information. So instead of having just one image, you have a film. You have a film, and in this instant, you can see that it's not just one static image, but it's actually look expressing embryos moving inside the abdominal cavity of the mouse. So by having temporal information, you actually have a complete understanding of the biological events happening during the 15-minute integration that you're doing. And this is really the capabilities of the Photon Imager system. Okay, so just to summarize, instead of doing an acquisition, wait in the dark, and then at the end you know whether your reporter has worked or not, with the Photon Imager system, you start your acquisition, you can observe the integration of the signal in real time, you can stop when you want, but you also can access the kinetic data, and you can create movies and quantify all your temporal information. Okay, so why is it important? And I will talk a little bit more about the importance of quantification using temporal information this afternoon. But here's a quick example where you're looking at two tumors which look like they have the same kind of signal, and if you were actually looking at the signal at the early phase of the integration, you would actually think that the two signals are the same. However, they're not, because here you're not measuring at the right time. You're forgetting that the enzyme kinetics of bioluminescence involves substrate diffusion through the tissue. So here, you are not at the steady state of the enzyme, and you're not monitoring enzyme activity, and therefore you're not measuring the difference in number of cells, but you're actually measuring the diffusion rate of the substrate to the enzyme. So what you need to do is quantify at the steady state. The steady state is in the late phase, and if you can do a window for quantification at the right place, you will see that there's a significant difference between the two signals. Okay, so I've talked about bioluminescence. So obviously our systems also do fluorescence imaging. There's a lot of requirements for near-infrared fluorescence imaging today, although I would argue that fluorescence is probably a less sensitive approach to bioluminescence for deep tissue and low intensity and low numbers of cells. But here we can do fluorescence, and we can do it using sets of 16 filters for excitation and 15 filters for emission, covering 400 to 900 nanometer visible range. So we can image any fluorescent marker from blue and GFE to near-infrared markers. And here's an example of the capabilities that we can do with spectral unmixing of various fluorescent compounds. Here we've got angiostamps, which is targeting alpha-beta integrins for tumor angiogenesis, and a transferrin receptor for TFR-mediated endocytosis. And you can see that we can separate the two signals either in vivo or ex vivo on the tumor section. So I mentioned that our systems are modular, and here I'm going to talk a bit about the modules. So the box standard system will allow you to do up to 10 mice in bioluminescence and fluorescence, but you can also add capabilities such as the 3D modules, the X-ray, the tomofluorescence, and the high-resolution Macrolens modules. So here's an example of the 3D module. It's true 3D, i.e. we collect the information from the four sides of the animal simultaneously. So you can have the left side, the back side, the front side collected on mirror sets, and all collected simultaneously onto the camera. So you can actually measure the kinetics of the signal on the four sides of the animal simultaneously. And then you can use fluorescence transillumination for 3D reconstruction of fluorescent signals as well. And this is then reconstructed in our analysis software, giving you 3D information and volumetric quantification of the signals. So here's an example of the analysis software platform, where you have your tools here, where you can select your regions of interest. This is the viewing window with your animal here. You have the sagittal, coronal, and lateral sections, which you can activate for slicing and looking at tomographic views. And here you've got an atlas, an overlaid atlas, to look at various organs that you can overlay to your bioluminescent signals. You can threshold the signal with the toolbar, so it's a very user-friendly software. And you can see here the slicing sections appearing by selecting the slices and the movement for quantification on here. So it's just a quick overview of how user-friendly the analysis software is. We also have the in-action module, as I mentioned. So the in-action module allows you to overlay the image of the moving mouse and quantify the bioluminescent signal in real time in non-anesthetized animals. We're using laser sets, so for excitation in infrared, with an infrared camera to collect the optical image, and then a dichroic mirror which will block any infrared light, so that we can collect all the luminescence information directly onto the ICTD, which will be placed above here. And we have a Macrolens module. The Macrolens module is a macrolens with X, Y, Z axis, piezoelectric guided for high precision, and you have a joystick on the outside of the machine to control the focus and the positioning of the samples. And here's an example of zebrafish imaged with the macrolens, looking at two fluorescence marker, sialic acid and propylium iodide. And another example here of a live Drosophila with a GFP labeled neuronal marker. And you can see the high resolution of the axons of the nerve endings going down the pose of the Drosophila. Here. We also have an X-ray module. The X-ray module will allow you to do correlation of the bioluminescence and fluorescence signal with the anatomical information from the bones using a flat panel, which is low dose and high sensitivity, high resolution X-ray sensor. So you can see here the phalanges of the paw of the animal, and we can do up to 5 animals in both bioluminescence and fluorescence. Here's a near-infrared marker for neospastic bone formation. You can see its localization in the joints here and in the paws of the animal. So we also have the 3D module. The 3D module can be combined with multimodal capabilities such as the MicroCT from MILAB, and you can correlate the 3D information with the anatomical information from other modalities. And finally, our tomofluorescence module, which is a laser dot by dot tomography fluorescence module, which allows you to quantify the volumetric information of fluorescence markers in deep tissue with high sensitivity and high resolution on a surface of about 2 centimeters square, and you will have a 3D tomographic reconstruction. Here you have an example of its applications, looking at the progression of mammary murine tumors in the lungs after implantations, looking at day 10, day 12, and day 14, and the increase in progression of the signal in the lungs. And here the quantification of it in diseased animals compared to healthy animals. And I will give you some more applications on this this afternoon. So really, it was a very quick introduction on the capabilities of our systems, and I hope you will be there this afternoon to look at more applications in detail.